some simple hardware-aware optimizations to CNNs. So CNNs have huge demands of computational power and memory accesses. That means when you try to run it on any processor, CPU, GPU, or any accelerator, it needs huge computational power and it needs huge number of memory accesses. So we broadly divide the optimization techniques into two types. One is compute related, another is memory related, and it is not that like it is compartmentalized. Some of the techniques will provide both the advantages. And here I will just discuss simple, like those optimizations which are very popular, and more specific techniques will be discussed in later lectures. Okay, so just 1 minute. Okay. So here are some compute-related optimization techniques. One is loop enrolling, loop pipelining, loop reordering. And if you remember, in the last class we had, it showed that how convolution involves multiple levels of nested loops. That's why loop optimizations can be applied on convolution operation. That's why here we have some loop optimizations. And how because it is compute-related optimization techniques, we will also discuss some technique for how to reduce the number of multiplications or additions. So one is factorized multiplication, another is changing the convolution strategy from GAM-based to FFT-based or Winograd-based. We will have a full lecture on this one. For this, we'll have a separate lecture on this. And these are some of the memory-related optimization techniques. One is called tiling or blocking. This is very popular or very commonly used. I will discuss it in a separate lecture, not in this lecture. Another is batching. Another is instead of using floating point number system, we can use fixed point representation. Then we can fuse the layer, CNN layer fusion, clustering, data compression, pruning. So we'll just introduce these. Now let us first discuss compute-related optimizations. So loop enrolling is simple. Suppose we have this original loop, which runs for 100 iterations. Here is G. Now it executes some function which is G. Now here I make this loop run only for 50 times, but in each iteration I run this G 2 times. That is like unrolling. Okay, this is loop unrolling. Now, what are the advantages and disadvantages? So so here of course it is G, so here it is not very visible. But suppose whichever function it is, if two iterations they can be done in parallel. That means if we have no data dependency, then we can exploit hardware parallelism. So if you remember in approximate computing, we discussed this example. So here what we can do, suppose this G and this G, we can simultaneously run them, right? We can do parallelization. We can suppose we can have either 2 GPUs or 2 CPUs or 2 FPGAs or 2 parts of the same FPGA. So one function G we can run, another function G we can run in parallel. And it reduces the number of loop controlling instructions and branch penalty. So if you forget this point, unless you know computer architecture. So here you can see that here I will need to run this for loop 100 times. And here I need to run this only 50 times. So the number of loop controlling instructions are less here. Right? It is less number of instructions here. The loop controlling instructions are less. However, but here I have more number of instructions for this part. Right? Here the number of static instructions for G is just once. But here all those instructions of G I repeat. So that means I reduce the number of instructions here, but I increase the number of instructions here. Okay, so that's why it will increase the binary size, because the same instruction I repeat here and here. And if previously my binary may be just suppose 4 megabyte, now my binary may become 8 megabyte or 6 megabytes. Okay, so this is not good if your memory is limited. Now, here, if you try to do parallelism, it will increase your hardware requirement. If you have sufficient hardware, it is good, you get parallelism. But if you don't have sufficient hardware, it will anyway not give you any performance improvement. And most important, sometimes it is not even possible to do loop unrolling. Your code may become less readable, and you may introduce a bug, right? You may introduce a bug because you may not realize that there was a dependency, but you can try to parallelize it. It leads to a bug. This is loop enrolling, and because our convolution has multiple levels of nest, I mean, any one of the loops we can unroll it, especially when this is a large value, especially when this n I equals to 0 to n. This n is a large value, then we can unroll it. So is it clear? Anyone has any question?
Sir, I have.
Yes, please go ahead.
Yeah. Sir, what is the difference between increase in hardware requirement and increase in computational requirement? Because what I see is computational requirement is equivalent to hardware.
Yeah, computation. See here, computation requirement has not changed between this and this. Computation requirement has not changed. But suppose you have 2 cores. Okay, suppose your processor has 2 cores. Now this part, now if you write the original code, then only one of the core is utilized, another core is not utilized. Although you have available computation capability, but you're not utilizing that capability. Whereas here, it may be possible that now this part you can easily run this G part on one core and this next G part on another core.
Sir, is there any way we can distribute this kind of thing to any core inside?
So how do we distribute that? That is called, like, for that we have parallel programming languages. So okay. I will in this course I'm not discussing it. I have offered a full course on that, and OpenMP, MPI, CUDA. CUDA I will discuss. I will discuss CUDA briefly, but I will not discuss other parallel programming languages. So how to distribute it, that is not important for us, right? Whether we can distribute, what are the advantages of distributing, what are the challenges of distributing, that's what we are discussing.
So just writing this code will distribute automatically, right, in the background?
No, I mean, generally it will not automatically distribute. Some compiler, you have to do something. So compiler will do it actually. You don't have to usually worry. If nowadays compilers are very intelligent, usually they can do it. Anyone else also had a question?
Sir, if the function is dependent on the loop variables, then this won't work.
Yeah. So when it works, when it doesn't work, that's a separate point. Yeah. So suppose here G is a function of I. Then here, so this is I and this is I. So this becomes wrong, right? So here you have to write I and I plus 1.
Okay.
Then it is possible. But if value of G I plus 1 depends on value of G, right? So then you cannot parallelize it. You can unroll it, but you cannot parallelize it.
Okay. Yes.
Sir, why we are executing G function 2 times in unrolled loop?
Because we have here you have right? I plus equals to 2 now. Here I was doing I plus plus. It is I plus equals to 2.
Suppose sir, value of I is 10. Suppose then it executes the G functions 2 times.
Yes. So how many times? So because you tell me how many times are we executing G here? Total number of times.
Total 100, sir.
And how many times here?
Here, sir. 50 maybe, sir. 50. I'm not sure, but 50.
No, why you are not sure? You can see, right? It's a simple. If you know C++ programming, then you can easily tell how many times are we executing G here. So here you said we are executing 100 times.
Yes, sir.
Here, how many times are we executing?
50, sir.
How come 50? See here 50, and each time we're executing it 2. So 50 into 2 is how much? 100. So both the codes are equivalent.
Okay, sir.
I've just written it differently so that this exposes the opportunity to parallelize it.
Okay, sir.
See, one extreme option is forget for loop. Just write the G 100 times. Isn't it possible? Possible, right? Nobody stops me.
Okay, sir. Sorry, I'm asking that for loop is going for 50 and G function
Yes.
is running 100 times. That I am
Yeah, G is getting executed 100 times.
Okay, sir.
And you can actually, as I said, you can throw away for loop, just write it 100 times, and you can easily parallelize it. But of course, then you can see your code will become unreadable. Nobody will understand it.
Sir, got it.
Okay, let us go on. If you have a question, you can ask later. Now, loop pipelining. So, loop enrolling and loop pipelining exploit parallelism between loop iterations. Both of them, they exploit parallelism between loop iterations. And here, the only difference is loop enrolling works when iterations of a loop are independent, whereas pipelining allows the next iteration to proceed even before an iteration is finished, as soon as this iteration can provide data to the next iteration. So, if you know pipelining, you will easily understand it. But if you don't know pipelining, let me explain a little bit. What is pipelining? So, what happens with the pipelining is that suppose you have to design a car. Okay, so in a car you will have multiple steps. For example, get the metal and put the shape and polish it. So let us just have 3 steps: polish, cast the iron, and get the iron or whatever metal you have. Next, for the next car, again you get the iron, cast it, and polish it. Then for the next, again you can get it, right? Cast it, polish it. So here you can see that some engineers will be doing getting, some engineers will be doing casting, some engineers will be doing polishing. So when first car has been, get or whatever first operation has been done, then those engineers are free. You can ask them to now get the next car. It is not that they have to wait. So if you don't do pipelining and you don't do parallelism, then what happens? Right? Get, cast, polish. Get, cast, polish. Get, cast, polish. So this will be the other option if you don't use pipeline. Okay. So I will give you one more example. Suppose we admit one batch of student in 2020. Okay. Suppose we are talking about BTech. So or any 4-year program. So first batch comes in 2020. Next batch comes in 2021. In 2021, the first year batch of 2020 has moved to now second year. In next year, the first batch will move to third year. The second batch will move to second year, and the third batch will move to the first year. Now imagine a case where we take only one batch in 4 years. So it's very good for faculty like us because only once in 4 years I will have to teach this course, right? So this is the first year 2020 batch. This is the 2020-24 batch. This is like Olympics, right? So only once in 4 years I will have to do something. So how much wastage of resources it is, right? How much wastage of resources it is. So that's why we do pipelines. That means as soon as the first batch finishes first year, we can admit one more batch, and then we can admit one more batch. So that is called pipelining. So here we can allow pipelining such that, so here now the same example you can think for the loop iteration. This is the loop iteration 0. This is the loop iteration 1. This is the loop iteration 2. So even before the first iteration has fully completed, I start doing the next iteration as soon as I get the data from the previous iteration. Right? Suppose my computations are dependent on the previous iteration, then hopefully they can provide the data even before that iteration is fully completed. So as soon as I get the data, I start the next iteration. So anyone has any question here? Okay, no question. I think it is simple. Now let us see the data storage patterns. We have 2 data storage patterns. One is called row major, another is column major. So consider multi-dimensional array. For example, we have this 2D array. Okay, and I show the elements of this as M00, 01, 02, 03, 10, 11, 12, 13, and so on. So this is my logical view. That means this is how I visualize my data as this is my view of 2D array. But the memory we have is just linear. I don't have a 2D memory. My memory is just linear. We have addresses, for example, going from 0 to suppose whatever 10,000 or whatever number. So the challenge is how do we store this 2D array in a 1D memory. So for this we have two options. One is called row major option, which is used in C, C++, and another is column major order, which is used in many languages like Fortran, MATLAB, Octave, R, and Scilab. So as I showed here, this is the logical view of a 2D matrix. Logical view means this is how I view it. It's not necessary. It is not the way it is stored in the memory, because my memory is after all 1D. How I store it in memory is like this. If it is a row major, if my memory storage pattern is row major, let us show this pattern first. Yeah. So row major, why it's called row major? I go to first row, then I come to the second row. I store the entire second row, then I come to third row. I store the entire third row. Okay. In the column major order, I first store the column, then I go to second column, that's column, then third column. This is how I do here. So here, as you can see, this is the yellow line, the yellow row. So first I store the first row, then I store the second row, then I store the third row, then I store the fourth row. Okay, and in the column major, I first store the first column. So yellow, red, blue, green. Yellow, red, blue, green. Yellow, red, blue, green. So then the next column, third column, fourth column. So in this way, I have been able to store a 2D matrix in a 1D array, or in a 1D memory. So if you have any question, please ask. Please make sure you understand it, because I will discuss tiling later on. If you don't understand it, you will not be able to understand the tiling part. So if you have questions, please let me know. Okay, I think it is simple. If you don't have questions, then let's go forward. Now, based on this, how do we do loop reordering or loop interchange? So what we do, we restructure the data layout or data access patterns. So suppose we have a column major order, right? Suppose I'm using MATLAB, where my storage pattern is column major. So what does column major means? So if you see in column major, xi plus 1j follows xij. So for example, you put I equals to 0. Suppose you put I equals to 0, j equals to 0. Then what we have is x. What we have is x, or let us call it m. Let us m 1 0 is close to m 0 0, and that's what it is here. M 1 0 is close to m 0 0. So xi plus 1j, it is close to xij. Okay. Whereas xij plus 1 is far away from xij. That means this and this, they are far from each other. This and this, they are far from each other. Right? Xij plus 1. That means, what does it mean? M01. These are very far away. Okay, you can see this is far away. Okay, so this is my given fact. So I'm telling you that we have stored the data in column major. Okay, now my question to you will come. So I'm calling that, given this column major layout, this code will be poor. Why? Why this code will have poor performance? So if you know a little bit about spatial locality or cache or computer architecture, you can answer it. If you don't know it, I will explain it. So just think that we have this code, and I'm telling you that this code will have poor performance. So can anybody think why this code will have poor performance? Sagar is not here. Sagar. Anubha, you know the answer?
No, sir.
Okay, anybody knows the answer? Okay.
So may I
Yes, sir. Anupam, let us allow Anupam. Yes, Anupam, please.
Sir, I feel like when the for loop will start, sir, I and j is 0, 0.
Okay,
And then
very
next,
good.
when the j column starts, sir, it is like M0, 0 and 0, 1 is far, sir. So every time 0, 1, 0, 2, it will go, it will has to traverse more, sir. Especially they are little apart.
Very nice, very nice. So I'll write, yeah. So see, very nicely answered. So yeah, I will answer now. You actually answered correctly. So what happens here? See, first I will access xij. So x, let us just call it m. X and m are same. So first, suppose I access 0, 0, 0, right? Now what happens? I will access 0, 1. So then I access this part. Okay, then j becomes 2. So I access 0, 2. So I access this part. Then I access 0, 3. Right? Then I access 0, 3. Okay. So now we can see that I'm accessing very, very far data items. I cannot fetch them in a single access. When I fetch this part, I will also probably be fetching some more items which are unnecessary. I fetch them, but I don't use them. I will have to discard them. I fetch all this, will not be used. I will have to discard it. Okay. Now, can anybody tell me, given the slide title, what I should do? Anyone except Anupam? Given the slide title, what I should do now to solve the problem?
Replace I by I plus
1. I by I plus plus.
1. I plus 1.
Replace the for loop.
Wait. First, Sai Vikas, please tell me what you are saying.
This is for column measure. Like as it is specific case, we need to replace with I plus 1 to allocate. I mean to next to retrieve M0 M10 element.
No, not only your answer is wrong, it is unclear also. And anybody else?
Sir, just interchange this for I and j columns. I mean this loops. Interchange these loops. So
Yeah,
it will
exactly.
go to loop column, then row. I mean first column, it will go through all the rows, and similarly like that. So
yeah, the better code will be here. You have to interchange the loop. That's what it is written: loop interchange or loop reordering. You need to for column measure order. You will have to first do j equals to I to columns. That means and then I equals to 1 to rows. So now let us see how it helps. So first we will access 0, 0, which is good. Now I will change. So it will be accessing 1, 0, then 2, 0, then 3, 0. So now you can see 1, 0 is here. So sorry, 0, 0 is here, 1, 0 is here, 2, 0 is here, 3, 0 is here. So all the elements I'm able to access sequentially. That means the elements I'm accessing are stored in a nearby location in the memory. So I can just make one access and fetch all of them. Okay. So is it clear for everyone? Is it clear to everyone? Okay. So now suppose my next, just let me ask a question, then you can ask a question. Suppose I were to use row measure order. Suppose instead of column measure order, suppose I were to use row measure order. Now, Gaurav, can you please tell me which of these, either left side or right side, which code will have better performance if I were to use row measure order?
I do not.
You don't know. Okay. Mohit?
Sir, left one, poor code.
Yeah. See, if you use row measure order, then this code will become good. This will become bad or poor code. Okay, so this is the converse property. So if it is a column measure order, then this code is better. If it is a row measure order, then we are accessing, we are accessing 0, 0, 0, 1, 0, 2, 0, 3. And as you can see in the row measure order, they are stored in nearby. So you can see 0, 0, 0, 1, 0, 2, 0, 3. So they are stored in nearby. We can fetch them all in one access. Now, anybody who has a question, please ask. Yeah. Okay, if you don't have question, let us go further. Okay, now there is a Winograd-based convolution. So I will discuss this in more detail. I will not fully describe the Winograd, but somewhat more detail later on. Compared to matrix, so GAM means generalized matrix multiplication. Okay, so this E is actually just added to make it a some good sounding word. Instead of calling it GMM, they call it GAM. So generalized matrix multiplication. So compared to GAM-based convolution, Winograd-based convolution reduces the number of multiplications at the cost of increasing the number of additions. And as we know, multiplications are much more costly than additions. So that's why, in some cases, Winograd-based convolution is more efficient than GAM-based convolution. Okay. Similarly, there is FFT-based convolution. So I think, do I have it here? No, I think here I don't have it here. I will have it in separate presentation. So FFT-based convolution also reduces the number of multiplications. So as you know, convolution in time domain is equivalent to multiplication in the frequency domain, and that's why we use this FFT-based convolution. But FFT-based convolution has this limitation that here we do the computations in complex domain. Okay, and it also uses large amount of temporary memory because we take the Fourier transform of the filters, we take the Fourier transform of the input, we multiply them element wise, then we get the answer. So whenever I'm doing element wise multiplication, both of my matrices should be of the same dimension. So here I have to pad the filters to be of the same size as the inputs, which is costly, especially when filters are smaller than images. So usually we have like 3x3 filters. Suppose I have 3x3 filter and my image is 224x224. Then I have to pad it. I have to make this also 224 into 224, which is very, very costly. That means I will have to have so much additional padding. Padding just means I put 0, 0, 0, 0 at the corners. Okay, there are some more limitations. I will just skip it for now. It will be too much to slide in the beginning. Later, it will become very clear to you. What is pruning will become very clear later on. That time I will show you this how FFT is not good for pruned CNNs. Okay, now let us discuss memory-related optimizations. So batching means is what? For improving throughput, multiple input frames or images can be concurrently processed. This is called batching. Okay. So as I give example before, see, one option is I have a CNN which does image classification. So either I can give suppose cat, dog, horse, cow, and so on, one after another, or another option is in one go itself I give all the 10 images I have, and in one go itself I will get all the 10 answers, separate answer for each image. So that's what I will here. The whole point is multiple images are simultaneously processed. Okay. So now how does it affect the computation? How does it affect the computation? So suppose I have some input vector. Okay, and this is the weight. So in convolution, we multiply input with the weight. Okay, so currently assume I am supplying only one input. So this is the left case is just I'm supplying one input. I multiply it with my weights. So if my input vector dimension is 1 cross 8192 and my weight dimensions are this, then I get an output vector of 1 into 4096 dimension. And currently it is a matrix vector multiplication. So this is a matrix, this is a vector. Yes. Question? Okay, so this is the matrix, this is the vector. So I perform a matrix vector multiplication. Once I do batching, I batch n images or n inputs. So now I get an output vector of dimension n into 4096. Okay, and now previously my computation was matrix vector multiplication. Now my computation becomes matrix multiplication. Okay, so now see previously, as you can see here, I think, okay. So batching converts a matrix vector multiplication operation into a matrix multiplication operation. Okay. So batching is useful for improving reuse of weights in FC layers. So we mentioned this point last time. Let us show how batching improves the data reuse. Okay. See here, I multiply this. So I assume you know how the matrix multiplication is performed. We take one row, we multiply it with one column. Then we take this row again, we multiply it with another column, then another column, another column, another column, another column, and so on. Okay. So can anybody tell me in this left part, how many times is each weight used? How many times am I reading a particular weight? How many times is it being used in any computation? Shubham. Akhil Kumar Reddy.
Sir, 4096 times. Hello.
No, that is wrong answer. Narendra.
Sir, each weight is used one time.
Very correct. Yes, correct. Yeah, each weight is read only once, because I see, as you can see, even from my lines that I've drawn, every weight I read only once. Input vector is used so many times. Okay, input vector is read so many times, but the weight is used only once. Now come here. I first take this first input. Suppose n equals to 4, just for the sake of simplicity, let us take n equals to 4. So now I do all the multiplication. Okay. Now for the second input, I further do the multiplication. Now for the third input, I again do the multiplication with all of these columns. Okay. And for the fourth input, I again do the multiplication. So now anybody can tell me how many times is each weight being reused?
4 times.
And times.
So Sai Vikas says 4 times. Narendra,
As
what
n
are you
is
saying?
as n is 4. Sir.
Yeah, n is 4. Yeah. So Narendra, you're saying something, or Prashant?
N times, sir.
N times. Okay, correct. Yeah. So here each weight is being used n times, and that is called a reuse. Okay. So we have improved the reuse of weights in FC layers by using batching. Okay. If we don't use batching, then there is no reuse of weights in the FC layers. But once we do batching, then reuse comes. But the point is, because batching may increase the latency, it is not suitable for latency critical applications. So although we are improving the throughput, but latency will also increase. So what is latency? What is throughput? This is a very important understanding. I will try to give an example of that later on. So suppose you, I think I gave the example of that either in this class or other class. So if I have 100 people working, okay, each of them doing their work in suppose 10 seconds. So in 10 seconds, I have 100 things done. Okay, 100 tasks in 10 seconds. Now just suppose I have very, very highly efficient people, but they also take a lot of salary. So I can only recruit 20 people. Okay, and they do their task in just 4 seconds. Or maybe let us take 2 seconds. Okay. So now how many tasks can I do in 10 seconds? At a time only 20 people can go. So in 10 seconds, how many tasks can I do?
100.
Yeah, 100 again, 100 tasks per second.
Hundreds.
100 tasks per 10 seconds. So In this case, my latency was 10 seconds. Here, my latency is 2 seconds, but the throughput is same. Right? Throughput is same in both cases. So throughput and latency, they are two different things. Throughput is the total amount of task that is done. And latency is the task, latency is the time that each task takes. Okay. So batching improves the throughput. That means instead of processing only one image, I am processing n images. Okay. But each image, but in processing of those 10 images now, or whatever n images, each image now takes more time. It is just like you're burdening somebody. You are asking him to do a lot of work. So he does a lot of work, but each work he does slowly, a little bit slowly. Okay, that's the idea. Okay, now we have CNN layer fusion. This is, this will require some more careful, attention. It's not so easy to understand. CNN layer fusion is more. But anybody has any question till this point? Layer fusion will require you to.
Yes, sir, I have.
Yes, please.
Sir, what is FFT convolution?
Yeah, actually, I will FFT-based convolution. I will explain to you. I will not go into mathematics of it, but I have a separate lecture. I think lecture number 6 or 7. That time we will discuss it in full detail. Here now we have just very briefly introduced. Some more details will give in lecture number, I think 6 or 7. Any other question? Okay, now let us see CNN layer fusion. So, what happens? We have CNN layers, right? We have suppose convolution layer, then ReLU layer, then pooling layer, then again convolution, pooling, ReLU. Okay, and we have all these layers. So what happens? We fuse the neighboring convolution layers or neighboring layers to avoid transfer of intermediate results between two layers. So on fusing multiple convolution layers, only input feature map of first layer are fetched from memory, and only output feature maps of last layer are written to memory. So here, what is the context? See, we have suppose some accelerator where we are doing, suppose we are doing just on CPU. So on CPU core is doing our convolution operation, and all my weights are stored in the memory. All my input is stored in the memory, and whatever outputs they are generated, that also I have to write to the memory, and whatever is the output of the intermediate layers, that also I will have to store in the memory because I don't have space. Suppose my CPU does not have sufficient space, so I have to store everything in the memory. Okay, so there are actually two types of execution patterns. One pattern is that suppose so you forget right now ReLU and pooling. So those you forget for now. Okay, let us just think we have convolution 1, C1, C2, C3, C4. Okay, so let us first think how the execution happens. So first fused layer generates outputs in the order that will be consumed by the next fused layer. Thus the data can be directly passed to the next layer without sending it to or from offchip. So I'll come back to it. See, here this was our layer 1. Okay, this is the input. Okay, here weights are not shown. I mean, what is the value of weight, that is not shown. But you can see this tile. So this tile with black boundary, that is tile 1. And the tile with red boundary, that is tile 2. Okay. Then I operate this tile. Okay. Then we get the output for tile 1 or tile 2. So this black one, which now is of smaller dimension, I get that part, and that's the output for tile 2. I get the second part. So that is output of tile 2. And this is intermediate feature map. That means it is the output of intermediate layer. This is the output of layer 1. Then I further process it. So finally, what will happen? I will just come to 1 pixel. So finally, I will have just 1 pixel in the final output layer, which if you go back and map, this was actually, this 1 pixel was generated by many layers of many layers of convolution. Okay, so starting from this single output location, if you track back and you trace backwards, you see the region of the input feature map it depends. So this feature depends on this black part, and this black part depends on this black part, Okay, this black boundary part, this part. So this is a computation pyramid. I hope this part at least you agree, right? Finally, we get just 1 pixel, but that 1 pixel was generated as probably 3 pixels, 5 pixels, 7 pixels, 9 pixels, 11 pixels. So we get a computation pyramid. Okay, so now there are two computation orders. One option is forget this layer completely. Just first execute the computation of this layer. First you generate. So this is the n. We have n feature maps. So first you compute first feature map, store its result somewhere else. Then you compute second feature map, store its result somewhere else. Then you finally come to n feature map, and then you start executing the next layer. You execute its first feature map, second feature map, nth feature map. That is one order. That means within this like C1, you execute its 0 to n minus 1. Or let us call it 1 to n. Right? So let me delete it. So first, if you don't do any fusion, suppose that means if you have no fusion, then you execute 1 to n for the layer 1. Then for layer 2, you do 1 to n. Then for layer 3 or whatever final layer, you do 1 to p. Okay, that is without fusion. But once you fuse it, then how you do? How do you change the execution pattern? You first do suppose L1. Okay, then you do it's layer 1. Or not sorry, it's a feature map 1. Then you come to layer 2, you do its feature map 1, and even in that feature map 1, you just do this part, just this type. Okay. And then you just go on here. And next you do the second tile. Then you do the second tile for this layer 1. And here we see that many of the computations are common between this tile and between tile 1 and tile 2. Most of the computations are common. You just need to have one extra layer, one extra column of computation that you have to do for tile 1, because convolution is a sliding window operation. So that's why whatever computations you have done for this tile 1, most of it will be reused for tile 2. Okay. So that's why this is how it works. Once input tile 1 black outline is loaded on chip, we compute entire pyramid of intermediate values without transferring any feature map data. Okay. So once we load this part, this black part, we just go on doing till here, till here. We compute this. That means you compute the pyramid first. Then you move to the next pyramid, which is situated at with this as the base. On reaching the end of fused layers, only values in the last output feature maps are retained. So after processing one pyramid, no need to load a full new pyramid. Just load one new column and discard the leftmost column of the old type. So here, what you do, you discard for the next type. You just discard this part and you load one more part. You just load one more part and do the computation for the next type. For the next tile, which starts the next pyramid. Now let us see here from the beginning. So we have to fuse two neighboring convolution layers. So that's what it is. This is one convolution layer, this second convolution layer. We are fusing them. So to avoid transfer of intermediate results between two layers. So here what happens? Actually, I deleted that part which you deleted. So here we did C1 layer 1. Layer 2, layer 3. We did this one completely 1 to n, 1 to n, 1 to p. So this was no fusion. So here what I have to do, when I generate the output of all these 1 to n layers, when I generate the output of this 1 to n layers, at the end of it, that time I start 1 to n. But because this is so much output, I will have to send it back to the memory because on chip I don't have sufficient space. Okay, so that's why and then I start processing of this layer 2, 1 to n. Then I store its result somewhere in the memory. Then for starting this one, I again fetch it back. So intermediate result I have to store because they become too much. Then I fetch it to the We fetch it again in layer 3 and then again start processing. So that leads to a lot of input and output from main memory to the on-chip. But in this fusion, only input feature map of first layer needs to be fetched and only the output feature map of last layer needs to be written. That means this intermediate, they are avoided. A first fused layer generates output in the order that will be consumed by the next fused layer. Okay, so that's why here we are generating, as I said, this tile-based ordering. First, I generate this tile and then do the computation for the whole of this pyramid. Then I generate this tile. So as you can see, this four into 4 column, 4 cross 4 thing, I can reuse, and that's why this transfer is reduced, because I am generating the output in the order that will be consumed by the next fused layer. Okay, so that's why I am doing the computation in a pyramid sequence. Once input tile 1 is loaded on chip, they compute entire pyramid of intermediate values without transferring any feature map to the output to the off-chip memory. And once I reach the end of fused layer, only values in the last output feature maps are retained. And after processing one pyramid, I just move the pyramid a little bit and load only one column instead of loading the whole column. So this reduces 95%. I mean, for this example which I have shown from this paper, Alwani's paper, it reduces 95% of the off-chip data transfer. But it reduces slightly extra amount of on-chip memory. So that part is also there. So I have tried my best to explain it. If you could not explain it, probably I will not try to explain it again. You try to read this paper yourself. If you understand it, is fine. If you don't understand it, is fine. We will not include any questions from this in the exam or in the homework. It's a difficult technique to understand. Actually, you have to really visualize how convolution happens. Slowly, that visualization will come for you. Okay. So some techniques are very simple. Some techniques are difficult. So we have to include, all of them. Okay. So fixed point versus floating point. Actually, I will skip it this time. I will have a full lecture on it. Okay, later on, I will have a full lecture on fixed point versus floating point format. That time, we will discuss it in full detail. So here I will just mention that fixed point hardware, the hardware for fixed point computation is cheaper or it has less overhead compared to the hardware for floating point format. So now, where is the scope for fixed point? Again, this will be fully clear once you understand the fixed point. But see, these concepts are so much interrelated, it's very difficult to decide which topic to discuss first. So some amount of CNN, some amount of basics, some amount of CNN, some amount of basics, both will to understand. So in neural networks, we use non-linear activation functions like tanh and sigmoid. So if you remember yesterday, we had discussed how the sigmoid had this kind of pattern. That means it saturates. Okay, it doesn't go infinity like value, it saturates. So it bounds the range of parameters. That means after this, even if whatever input you have, it will be clipped. It will not go more than that. So already you have bound the range of parameters. That's why if you now use fixed point, you don't get further loss in accuracy. There is no loss in accuracy. And neural networks are used for error tolerant applications. Anyway, we have discussed this in great detail, approximate computing. So if you use fixed point, there will be some accuracy loss, but that is tolerable. Okay. Next comes data compression. So the CNN weights, they are computed in the training phase. During the inference phase, inference is also called testing or serving. During inference phase, the weights do not change. What we can do, we can store these parameters in compressed form. We will not discuss data compression in great detail, or any detail, but at least everybody knows what is compression, right? If you have a 10 MB file, you reduce it to 2 MB by using some compression. That's called data compression. So we can store these parameters in compressed form, and then at runtime, we can decompress it. So compression is performed offline. What do we mean by offline? That means after training and before inference, you have sufficient amount of time. That time you can do the compression. So even if it is low compression, it is fine. And you can use compression algorithms which have high compression ratio. There are many compression algorithms like low overhead. These compression algorithms should have low overhead and low latency of decompression, because at runtime you will decompress it. That means while you are doing inference, you will decompress it. Decompression takes some latency. Okay, so you need to keep the latency of decompression low. Otherwise, your inference latency will increase, which is not what you want. Finally, pruning. Hopefully, we can complete it today. So pruning here, I will again discuss pruning in full detail later on. So pruning removes the weights which are small or which are close to zero. Okay, some weights are very small, so anyway they don't have much impact. So what we can do, we can just prune them or remove them. So that's called pruning. And then we can do retraining to refine the weights. So after here, this synapses, we can prune them, or we can even prune the neurons. Some of the weights may be completely removed, so there will be no connections between this and this. So we can just prune this neuron also. And remaining weights, we can do retraining. If you remember in approximate computing, I use this word that we can do retraining. Retraining heals the network. So retraining can refine the weights. That means other weights which are not pruned, their values may be slightly adjusted so that the final answer remains the same.
Sir,
yes.
Is pruning like nodal droppings?
Pruning like neuron dropping. So there is actually pruning of the weights and there is a pruning of neurons. These are two different things.
Yes, sir.
So once you prune sufficient number of neurons, it may happen that once you prune sufficient number of weights, it may happen that some of the neurons have no inputs. They have become ineffective. Right? For example, here we have pruned this neuron. Why? Because all these weights, they were removed. That means there is no influence from this layer to this layer. Okay. Now this is a leveraging locality in memory graphing. So this is how we actually do the computation. From DRAM, DRAM is off chip. We bring the data to memory buffer. Then we bring the data on chip, where we do the computation, and whatever output is there, we actually write it back to the main memory again. Okay. So here, because see, we don't want to all the time go to the DRAM. DRAM access is very, very costly. So what we do, we keep a on-chip buffer, right? Which we can call cache or scratch pad or shared memory or some global buffer. There are different names for it. So we have actually temporal reuse because the same data is used more than once by the same consumer, right? So if you remember, we said this, that batching improves the reuse, right here. So batching improves the reuse, which means that if you have batching, then the same weight is reused again and again. So instead of all the time, instead of fetching it n times from the DRAM, we can just store it once in the on-chip and then reuse it. Okay. So that's the idea. So, and there is a spatial reuse. The same data is used by more than one consumer at different spatial locations of the hardware. Actually, spatial reuse is slightly different also. So spatial reuse means like array. When you are accessing array, once you access the first array element, you also most likely access the next array element and the next array element. So that means the elements that you are accessing, they are nearby in the memory. Okay, they are located nearby in the memory. So that is called spatial reuse. And here this is another definition of spatial reuse. So there could be like lot of cores. Okay, so you can bring the data to one core, pass it to the next core, then to the next core, then to the next core. So you will see this pattern in the systolic array. And I think this is my last slide. Oh, actually, there are many more slides, so I think we'll stop here. We will stop here today. I will discuss the double buffering next time. So if you have any question in any of this, except that layer fusion, you can please ask.